Welcome to another tutorial based on the Sedra Smith book. The topic will be current mirrors. Since we've covered what a diode connected MOSFET is, or in this case drain to gate to drain MOSFET, we see it right there. Okay. And when we see a gate drain connected MOSFET, you have to know that what M1 is doing, or the gate drain connected MOSFET is doing, is actually setting up a bias. Okay. And when I say bias, it's more like the DC voltage, DC operating voltage. And basically it's setting the voltage right here, this VG. Okay, so basically you're going to have a VGS from there to there, and that voltage is placed on this M2. Okay, so M1 is a bias. Then what is M2? Well, M2 is the mirror. Okay, so basically if these two MOSFETs are equal, M1 and M2, and when I say equal, the same, equal in that they have the same width, and also if they have the same length. Okay. Well, if they're equal, then whatever current is flowing on the mirror side, or actually on the gate drain side MOSFET, is going to get copied or mirrored on the M2 side. Okay. For example, in this situation, or in this example, I have 20 microamps. Okay. If both are equal, then you're going to have the same current. Okay. And the reason is because they both have the same gate voltage. Okay, so whatever voltage the M1 has from gate to source, well, that is the same voltage that you will have across the gate to source of M2. Okay, so basically they're going to have the same current. Okay, well, what happens if they're not equal? Let's say that this is bigger. Okay, and let's say that it's 5 times bigger, which is what I'm saying right here. Let's say that M2 is 5 microns, and let's say the width of M1 is 1 micron. So you have a basically 5 times bigger MOSFET. And let's assume that L1, length of M1, is the same as the length of M2. So we'll use that assumption. Okay. So what happens? Okay. Well, what you can do, you can set up a voltage relationship. Okay. You can say that the width of MOSFET 1 divided by Iref, which is the current that is flowing through N1, okay, is equal to the width of 2, this one, divided by I out. Okay, so basically we want to know what's going to happen if I out. What is I out if M2 is 5 times bigger? Okay, so in this case you can solve this for I out. Okay, so now you have this equation. Let me erase that. Okay, so now you can kind of plug in say the I out, and since W2 is 5 microns, okay, W1 is 1 micron. Okay, that cancels. So basically, and if I ref is, this case in our example is 20 microamps, then we have a I out that's 500 microamps. Okay, so you can see that it mirrors, but it also scales. Okay, now what else can you do? Well, you can actually put a bunch of these. Okay, let's say we put another, let's say we extend that voltage, or yeah, that connection, and let's say we put another MOSFET here. You can put a whole series of MOSFETs here, and let's say this is 10 microns. Okay, then the current flowing here would be 10 times 20, because since it's 10 put a M here, 10 microns, and remember this is 1 micron. It's 10 times bigger, so that means that the current flowing through this transistor will be 10 times bigger. So that would be 200 microamps, and so forth. Okay, and basically you can have a whole slew, and you can have different currents, and all of those are controlled by one MOSFET. Okay, so this is a very basic circuit that is used in integrated circuits. And you can also have this situation. You can, since those are N channels, you can have a situation where you have a current source, and of course you have your gate drain connected MOSFET, and you have your mirror. Okay, and these are N channels. Then you can have that power a P channel. Let's say this is VDD. Okay, so same situation. Let's say you have 10 microamps, and let's say this has a width of 1, it has a width of 2 microns, no, let's say 5 microns. So in this case the current through here will be 50. Okay, that current flows through here, also has to flow through here. Okay, and one thing that I wanted to point out is that you can also have a P channel current mirror. So here's your gate drain connected MOSFET, and here's your mirror. Okay. Now, one thing that's important to know, that the P channels, if you keep the same VGS, the same current, okay, they're going to be approximately 3 times bigger than the N channel. Okay. And you might ask, well, why? Okay. Well, the reason that they're 3 times bigger for the same current is that N channels, the majority carriers are electrons. Okay. And the majority carrier, a P, are the holes. Okay. And between the holes and the electrons have less mass. Okay. And these are more mass. So you probably say, well, so what? Well, that means that these are faster because of the less mass. You have less force, so they move a lot faster. And since these holes have more mass, they move slower. Okay. So how does it manifest as far as current? Well, when you look at the Kp of a P channel, which is a transconductance process, there's a Kp for the P channel. Okay, and there's a Kp for the N channel. Okay. When you look at those parameters, these Kp channel, is typically 3 times, or it's a third, 1/3 as much as N channel, or you can say that this is 3 times bigger. Okay, and the units are amps per volt squared. Amps per volt square. Okay, so knowing that, okay, you have ID, and let's say Kp P W 2x VGS minus VT. Okay, so this is for a P channel. ID N Kp N W 2L, and just bear with me, you'll see why they're bigger. Okay, so if this is a third right there, if Kp is a third, then for the same current, W has to be 3 times as big. Okay, so that's why this Kp comes from that the holes are much bigger and you have a Kp that's much smaller. So since your Kp is smaller, then you have to make the width 3 times bigger. Okay, so that being said, if you have this at 5 microns, that means that this has to be 3 times bigger. So that would be 15 microns. Okay, so then you use the same scaling. If this is, let's say, 30, this is 2 times bigger than this MOSFET. So, and since this MOSFET has 50 microamps going through here, that means the current flowing through this MOSFET it's going to be twice as big, so you would have 100 microamps. Okay, so hopefully that explains that. Okay. Another subject that's important, and typically they test you on this on the exams, is a typical question that they always ask is if you have a current mirror, okay, this is just one current mirror, a simple one. Okay. Let's put that, and we'll say IOT, IRF. Okay. One of the questions that they'll ask is, what is the impedance? And it's pretty straightforward. It should be RO. Okay. Now, one of the things that drawbacks of using just a single is that the impedance is R out. Okay, and depending how high R out, you may have a current source that changes with VDS. Okay, what do I mean by that? Okay, let's do this. If you plot the current, we all know that if it's ideal, it goes to the triode, and then it's supposed to flatten straight like that. Okay, so if this has no slope, that means that RO is infinity. Okay, high input impedance. However, that is not the case. Okay, most of the time, let's see, where am I? Most of the time, you're going to have a slope associated with that. Okay, and on the previous video that I did on, I believe on diode, or actually gate drain, I had mentioned that this slope, the reciprocal of the slope, is RO. Okay, so that's important to know. Okay, and then another question that they often ask, what is the Vout minimum? Okay, so when you see that, your first inclination would be that it's a VDSAT. Okay, another I've heard it or read that it's also known as VOV, the overvoltage is another. So these are the terms that they typically tell you or refer to. Now VDSAT comes from this equation. Okay, so basically you're gonna have a VOV, you can call it, between there and there. That would be the absolute minimum. Okay, now what is common to circumvent this, in other words, since you have a slope, if you notice, depending where your VDS, in other words, whatever this voltage is at the drain, you might be operating, let's say right here, and let's say this is, let's pretend that this is, they're both equal, and let's say this is 10 microamps, and this is also 10 microamps. Okay, let's say at this, and then that means that this is 10 microamps. If your VDS is, let's pretend that this is connected to 5 volts, and let's say you're close to the 5 volt line. This is 5 volts. Okay, and let's say this is 2.5. Let's say that the drain is at 5 volts. Then when you plot, you'll notice that there's a delta. Is not 10 microamps, it may be 15 microamps. And let's say your voltage changes again, and you're right there, and you see that now it's maybe 12.5 microamps. Okay, and then you come over here and you're at VDSAT. That's close to VDSAT, and now you're at 10 microamps. So you notice that depending where your drain voltage, you might get a different ID. Okay, so this is kind of bad because you really don't want this type of variation. Okay, you want something consistent. So this slope in the transistor is a problem. Okay, so how do you get rid of that? Okay, well, the solution is they do a cascade mirror. This is the same thing. It's a mirror. These are your drain or gate drain connected MOSFETs, and these are your mirrors. Okay. Now when you look in here, okay, the output impedance, or I'll say Z out, is the exact equation, and let's say this is M1, M2, then the output impedance is RO1 plus RO2 plus GM times the product of both ROs. Okay, so typically the resistance of each gets multiplied. It's a squared. So basically you can simplify and say that it's RO naught square. So what that does is it gives you a more flat response. It takes away this slope. It makes it a little bit more ideal. Okay, so where previously we had a slope, with this configuration we end up with a more ideal case. In other words, it flattens out. Okay, so now this approach is more it's more ideal. Okay, so now if you notice, you can operate here or here or here, and you're still going to have basically no variation, no delta in the ID flowing through that. Okay, so that's very important to know, that because you cascade them, it infinitely increases the resistance, and through that action it makes the slope of this flat, and it gets rid of the variations that we saw by using just one. And typically, if you look at some of the MOSFET designs, some of the application notes, sometimes they'll show the schematic, and you'll see that a lot of the MOSFETs or op amps have this configuration. Okay. Now the only thing, it does have a disadvantage. Okay, and this is one of the disadvantages that it has. Okay. To illustrate, let's do a cascode, a true cascode. Okay. Now let's say that they're connected to a resistor network. So you're able to adjust what this voltage is, let's say V1, V2, and so forth. Okay. Now, Vout minimum, when you look at something like this, you should already say that, well, I'm going to need a VDSAT across that transistor and another delta VDSAT across that. So the minimum voltage should be 2 VDSATs. Okay. And let's go ahead and put some numbers. Let's say that we want a VDSAT of 0.2, and let's say VT equals 0.5. Okay. So if that's the case, that means that this voltage, let's say that the minimum voltage would be 2 VDSATs, which would be 2 of these. So that means you would have 0.4 volts. That would be anything above that. It means that you're in saturation. So anything above 0.4, it's in saturation, which is good. Anything below 4.4, it's in triode. And then you lose all amplification, no gain, basically. It actually acts as a resistor. Okay, and when it's in saturation, you have gain because you have a current source. And of course, that's in parallel with RO. Okay. So one equation that you can use to calculate what the voltage is, instead of adding the voltages and so forth, you can use this equation, which is VDS VGS minus VT, and you can break this up into this equation. I'm sorry. Okay, decided to act up now. Okay. You can break the VDS and VGS like so. So if you bring this to the other, no, sorry. If this bring to the other side, these cancel. So you end up with VD, VG, VT. Okay. So in this case, we know what VD is right here. and we're going to see what VG is. So we can say VG is VD plus VT. Okay, so we know that VD is 0.4. Okay, and then VT is half a volt. So that means for VG to be able to satisfy the minimum voltage, you have to set VG to 0.9. Okay, so that would be 0.9 volts. Okay. And by the same token, you can do the same thing. You know that this is 0.2. Okay. Same thing. You have 0.2 plus 0.5 volts. Okay. So that means you would have 0.7. So you have 0.7 volts. So if you set these two voltages to 0.7 and 0.9, then you are assured that you can go all the way to 0.4 volts and satisfy this equation. In other words, 0.4 would be the absolute minimum voltage that that you can swing. Well, what does that mean? Well, let's say if we were to plot, and let's say you're operating at a certain voltage, and your signal swings up and swings down. You can have a sine wave like this. Okay. Well, the Vout minimum is this point. Vout min. Okay. And in this case, in this example, we said that it's 0.4. Okay. So anything or anytime the signal goes below the 0.4, you're in the triode region. And anything above that is the saturation region. Okay. Well, how does that relate to the Cascode mirror? Okay. Well, now that you have that, then it makes understanding this concept a little bit easier, or at least I hope it's easier. Okay. So this is a drawback of using a Cascode mirror. Okay. So now Vout minimum, okay, question mark. Okay, now we know up here the Vout minimum is 2 VD-sat. Okay, and looking in here, you would say, well, I would be inclined to say that it would be 2 VDS-sat as well. But if you said that, if you were to say that, that is wrong. It's not 2 VD-sats. That's the drawback. Okay. The correct answer is Vout min is equal to 2 VD sats plus a VT voltage. So you actually have this extra term. or it's an extra voltage. Okay, so let's see how we can derive this. How do we prove this statement that I just said? Okay, well, first of all, let's calculate this VGS 1. Okay, so we use the regular equation, and I'll say that it's VGS 1 plus VT. Okay, and since the voltage is going to be from the drain to the gate, we can solve this and say that it's VGS 1 is equal to VDS minus VT. I'm sorry, should be plus. Should be minus, so flip to the other side, so it's plus. Okay, so that means that at this point you have VDS plus a VT. Okay, now you have the same situation here. You have VGS 2. Okay, so now at this point, and VGS 2 is also VDS plus a VT. Okay, that means at this point then you have 2 VDS plus 2 VTs. Basically you have this. Okay, you have a VDS plus VT from this point to that point, and then you also have another VDS plus VT from there to there. So the total VDS plus VT is right there. Okay. Okay. So now we can label this now. Say this is VG2. Okay, and we can say VG2 is equal to 2 VDS plus 2 VT. Okay, we're almost there. Okay, so now we want to know what is VD2. Okay, so we can use the equation that I had derived before, where it's VD is equal to VG minus VT. Okay, so we can also now name it VDS2 VGS2 minus VT. Okay, with that being said, now we can substitute this into here. Okay, so VD2, and now we can rename this. We can say this VD2 is actually V out minimum, and then we're going to put this term, which is 2 VDS plus 2 VT. Okay, so that's that, and then minus VT. So now we end up, or we proved that the V out minimum is 2 VDS sats. There's a 1 here, so that leaves you with 1 VT, and that's the answer. That's the proof. So basically it proves that you have an extra term in here. So what's the big deal? Okay, Well, what it does, where you're using a regular Cascode, or you have this voltage, now you have an extra term, meaning that you're eating up into the range that you can use this current mirror. Okay, whereas here you had two VDS sats, here you have two VD sats plus a VT. So now you have this little delta, that's a delta VT. Okay, I know this is a lot, and perhaps I should have made some broken it up in 2 videos, but hopefully I explained it well enough that it made a little bit of sense. If not, send me your emails, or post you can send them to my regular email at arbola35618 at AOL.com, or you can post them on YouTube. Thank you for watching, and hopefully these were useful.